Good morning, everyone. Welcome to the last day of the summer school. I hope you are enjoying. Later on, during the morning, we will send you an email about feedback form that you should fulfill in order for us to see if everything went okay and what can we improve in future editions. Okay. Today, it's my great pleasure to introduce you Desmond Elliott, an associate professor at the University of Copenhagen, where he leads a group that is currently focusing on tokenization-free language models and multilingual and multimodal processing. Desmond has a very high number of publications in very prestigious venues with some best paper awards, and his funding, his research is funded by many, a few organizations such as Google and Facebook and many others. I hope you enjoy. He will be presenting a lecture on vision and language. I hope you enjoy. Thanks.
Can you hear me at the back? Great. Thank you for such a warm welcome. And thank you for showing up on a Friday morning. I know it's been a long week, and we're almost at the end. There's just 3 hours of lecture and 3 hours of labs and a great evening lecture by Sarah Hooker at 5 p.m. But we're going to get there together. So this QR code will take you to the slides. If you have a device and you want to use that to annotate the slides while you're going along, please feel free to do so. I guess we will collectively take down the Technico guest network if we do this at the same time, but it's a risk I'm willing to take. I'm going to talk about vision and language learning, and I'm going to start with a definition that a vision and language model is essentially a special case of a multimodal model. And this is something that jointly processes information from 2 or more input modalities. For example, images and text, or speech and video, or images and speech. And you mix it together in the biggest neural network you can fit on your laptop or your GPU cluster, and you hope it produces the correct outputs at the end. But why would we be interested in multimodality? It's because there's quite a lot of evidence about how humans ground conceptual knowledge in modality-specific and modality-shared processing systems in the brain. This is an image from a famous study by Pulvermuller and colleagues about how when on the left-hand side, people are performing physical movement actions related to in blue foot movements, in red finger movements, or in green tongue movements, there is some co-activation in exactly the same locations of the brain when they're reading about these parts of the body. And there's actually much more evidence than this, but I think it's a very compelling starting point for why we should want to do this. And from a personal experience, maybe all of you have this as well, multimodality can reduce ambiguity. I saw this about 7 or 8 years ago in the airport in Edinburgh. And as a human being, I was able to quickly understand what this meant. But if I was a state-of-the-art robot, for example, the new one released by Hugging Face last week, or maybe a 1980s Johnny Five style robot, I would be a bit confused about what I was being instructed to do here. Do you want me to put my cigarette butt here or my pink butt? And it turns out if you can do more than just read text, you're able to recognize that there are cigarette butts all around this, and that if you sat on this with your actual butt, you would be very unhappy. But as Johnny Five is a robot, he doesn't care about that. And this leads more generally into the idea that you cannot learn language from text alone. In 2020, Bisk and colleagues had a very compelling argument about the problem with learning language models from only collections of text. And so most work started in the center of this at the corpus level. What we actually do today when we train large language models is we learn from the internet. And the claim from this position paper is that You can't really learn about language from radio just by passively consuming it because you also lack perception of what's happening on the other side. If you want to go a bit further and try to learn about language from television, well, this is hard because you are doing this as an unembodied agent. You have no ability to affect things, and so you don't know how other agents in the television show would act towards you. And this leads into the final scope here, where if you try to learn language without interacting with other people, then you're missing this kind of social aspect of human communication. Most of the work we see is to the left-hand side in the corpus and the internet, but over the last few years, we have actually seen things go a little bit towards the right. And I think that's quite promising for language learning in general. In terms of multimodal vision and language, there are at least 5 major areas of research you could be interested in: the representation of data, the translation of data between modalities, the alignment of data through modality-specific neural nets, fusing features together, and co-learning. In terms of representation, we've seen a lot of work in the last 20 years, going from handcrafted features like SIFT and HOG, all the way up to I'll just throw it through CLIP and use the CLS output embedding. In terms of translation, in the early 2010s or the mid 2010s, we saw this breakthrough paper by Vinyals and colleagues, Show and Tell, where they trained a neural network end to end with a ConvNet to produce sentences using an RNN. This was a breakthrough at the time, and many other groups had exactly the same idea. It came directly on the back of the sequence-to-sequence modeling by Sutskever and colleagues. More recently, in the early 20s, we saw methods for going in the reverse direction with things like Stable Diffusion, taking text as an input and producing pixels as an output. In terms of alignment, this has been very important for self-supervised learning. So models like CLIP rely on trying to learn alignments between modalities, but it can also be really useful for phrase grounding. So it's not just an elephant, it's the pink elephant, and I want you to tell me where this is. This is useful for downstream applications. In terms of the fusion of features, there was a lot of work on trying to develop either early fusion or late fusion architectures. What we actually have now is what I would call model-based fusion, where we feed all of the data into a transformer and we ask multi-head self-attention to resolve all of the different ambiguities and to throw away inputs that are not useful. And finally, in terms of co-learning, I think one of the most interesting applications for vision and language models is doing zero-shot transfer across modalities, where you can't observe the full joint distribution of vision and language, mostly due to sample bias and the fact that we just don't have enough input data. And so I think there's some really exciting work in that direction. But instead of taking a research-oriented perspective this morning, we're going to take more of a building blocks perspective. So throughout this lecture, I'm going to be talking about what I think are the core ideas in vision and language modeling and how they all come together. So we'll typically have some kind of data that's the input, and this black box is going to be our vision and language model together, which, according to the fashion in 2025, we're going to have a vision encoder, and we're going to have a pre-trained language model, and we're going to learn some kind of connector between those two models. And we're going to try and do this for some kind of task that we have in mind. So we'll start by talking about data sets and tasks for multimodal learning, because this is the thing we do before we even try to use a model. And I'll also share some reflections on some projects we worked on along the way, so that I can give you a combination of educational material and also some perhaps sometimes harsh reflections on work that we've done, so that I can be mean about my own work without being mean about what other people have done. In terms of data representation, I'll speak about what I think is some of the most important things to know about how we represent visual inputs. I'll also talk about modeling techniques. So how do we actually build these vision and language models? What are the main strategies? What are some of the things we don't yet know? And what do we want to do with these models once we have them? Then I'll speak a little bit about work on understanding these multimodal models. and going beyond accuracy-based metrics. And I'll also talk about some future directions that go beyond where we are right now in terms of research towards what I think we could be working on in the future. So that's the roadmap. At 10:30, we'll have a break, and I don't know where we'll be at 10:30. As most of you know, we had a late start because it turns out we just couldn't connect all the devices together. So we'll try to finish at a reasonable spot so we can have coffee together. Right, let's move forward. Data sets and tasks for multimodal vision and language learning. Jack Morris wrote a very interesting article on Substack recently that there are no new ideas in AI. There are only new data sets, and argued that LLMs have been developed in four major developments, and these are not actually algorithmic developments, they rely on data sets. And as a good scientist, I only look for evidence that supports my argument, so I'm happy to take Jack Morris as the inspiration for this part of the lecture. I believe there are two basic types of resource. There are those that are mined from existing data sources, like these massive trucks in the countryside. I don't know where this is, perhaps Australia. Or there are data sets and resources that we create from scratch, carefully planting the seeds and harvesting what we reap. And I'm going to work with this analogy throughout the first part of this lecture. I think that there are four main types of dataset creators. If any of you have any experience in making datasets, you might identify with one of these stereotypes, or you might see this when you think about the work of others. So on the data miner extreme, this cute little dude is involved in large-scale extraction of resources from wherever they can harvest them. We have the detectorist data type. This is the type of person who is interested in the focused search for artifacts that really match their needs and their interests. They're not going to dredge up large parts of the countryside for what they're looking for. We also have the permaculturist, which is a gardening type, who's interested in very minimal intervention. They want to just see how their garden flows based on what suits the environment they have. And then the final example is the Baroque gardener who will painstakingly tear up and manipulate the land to produce perfect installations of grass and trees and plants and water features. They will do everything possible to achieve this goal. And I think I've been involved in three of these types of dataset creation processes. I'm not yet a data miner myself. And I think that there are five key factors that are important when creating resources. There's the scope of the data you want to create. There's the relationship between you as a creator and the annotators. And then interleaved with each other, there's also a collection of images you want to collect and the texts that go along with it. And then finally, there's this factor about how tightly related the text and images are in terms of their binding. And I'm going to motivate all of this with some use cases. So back in 2015, we created a dataset called Marvel, which is the first dataset for multilingual multimodal understanding for English and German. This was multi-30K. And then in 2021, we created Marvel, which is a dataset for understanding visual reasoning across different languages and cultures, which is now a huge area of interest in research in NLP. In 2024, we worked on something called Foodie QA, which was a very deep dive into understanding Chinese food cuisine. And more recently, we worked on a project to do in-language exam evaluation using multimodal exams collected through an exciting open science collaboration with the University of Buenos Aires, Cohere Labs, and about 50 amazing volunteers through Discord. So let's go through some of these key factors. In terms of scope, if you want to collect or to try to understand the data set you're working with, you could think about what type of data were they trying to collect? Does it come from a broad collection of concepts or domains, or is it a very deep dive into a narrow and specific idea? So things like the Lion dataset or the Wikipedia image text dataset, these are really broad scope in terms of what they have in them. Lion hoovers up the internet from WAC files, Whereas something like Foodie QA was a really narrow focused dive into Chinese food cuisine. No other type of food made it into this data set. Whereas Kaleidoscope was more of a detectorist approach where we knew exactly what we wanted. It was in-language exams and nothing else. And there's also a notion of what types of tasks you want to collect this data for. It could be sequence generation, where maybe you want to model sentences given images, or maybe you want to do multi-choice question answering, in which case you're modeling a slightly different distribution than natural language. It could be that you're collecting it for a question answering task, or maybe you're interested in retrieval, so you want to model the distance between representations given the inputs. And so looking back, our focus in the Multi30K project was to replicate an existing data set. It existed in English. We wanted to recreate it in German. We replicated, to the best of our degree, every single thing from the English data collection to minimize the differences between the data that we received from our crowd workers. In terms of Marvel, our scope here was to try to go beyond the concepts represented in ImageNet. ImageNet is by far one of the most influential datasets that exists in machine learning, but it's based on an English taxonomic hierarchy of language. And so if you want to try to understand other concepts in the world, it's maybe not the best place to start. In terms of Foodie QA, we were really interested in fine-grained Chinese food understanding. The student that led this project worked with other Chinese speakers to create an extremely fine-grained taxonomic representation of things like how a dish was presented, or whether it's served cold or warm, or which type of cuisine it is, and what type of category this is. This is the type of fine-grained understanding that requires expert knowledge to create, but it also pushes models to demonstrate their expert knowledge and understanding. And in terms of Kaleidoscope, we really wanted to go beyond things like MMMU Pro, where we were mostly doing exam understanding in English, to understanding the gaps in models when looking at different languages around the world. In terms of the relationship between the annotators and the people who are actually collecting the data, I think that there's a lot of interesting gray zone here. Most of the things I try to think about are whether you're working together towards a shared goal, or whether the annotators are hired to perform a task that they ultimately don't care about. And so on the left-hand side of this, we have a collection of data sets where the people were hired and paid money through platforms like Crowdflower or Mechanical Turk. There's also this gap in the middle on purely volunteer-based dataset creation. I couldn't find any examples of that. So if anyone thinks they know of something, please let me know, and I can fill in the gap in this slide. There's also this approach of trying to be involved as a collaborator in a project. So in Kaleidoscope, we welcomed data contributions from around the world through a Discord server that Cohere Labs runs. And if people contributed above a certain minimum threshold, we invited them to be collaborators on the scientific article. And I think that's a really interesting way of structuring how you collaborate with people, because it gives a different incentive to paying people for a task they don't care about. And finally, I struggled a lot with labeling this one. I think Lion, where you scrape data out of WAC files, this is kind of like an indirect relationship, because the data that you get in something like Lion was not created for the purpose of vision language learning. It was created because somebody wanted to write something on the internet, and then at a later point in time, somebody else harvested it out. Maybe there's a better label. If you have an idea, please let me know. So looking at the annotator relationships, you probably can't read this at the back, so I'll go through it. When we were collecting the Multi30K dataset, I made some pretty stupid mistakes. The first mistake is I put this task on Mechanical Turk, no, Crowdflower. It was called Figure 8. I don't know. These platforms change names every 6 to 12 months. I put this on the internet every day for 30 days in a row, which was a massive mistake because I wasn't giving people a break. And we managed to find a web forum where people were talking about our task because crowd workers organize themselves in a way that they can understand who are good task initiators and bad task initiators. And so these people are talking about how the task we put online is really great for German speakers because they don't get much work. And somebody here in the middle writes, I only managed to do 40 of them today. We had a limit of 50 per day per person. But they also speak about how they have a system to work on the task because the task is so boring. So they do 25 examples, and then they take a 15-minute pause, and then they come back and they hope there's still another 25 examples left. But it turns out the task is so popular that sometimes it's gone within 45 minutes. And so they don't always get what they want. The final person here writes about how this crowdsourcing task kind of mentally affected their life. So they talk about how at the one point during the task, they realized as they were cooking dinner, they were imagining they were doing the task. So they were describing the food in their pan and what it looked like as if they were writing a sentence for 5 cents. And I think that's really unfortunate that the way we tried to do this data collection was having a mental impact on this person. We also found that people were also speculating about our intentions. They didn't know who I was. I didn't announce myself, but they could see my name as the person collecting the data. And they thought that this was because I wanted to know how different people perceive images, or that perhaps the project was something to do with AI. And somebody says that yes, they agree with that. And I looked at where this person is employed and I looked at their webpage. And so when you are crowdsourcing data, people want to know a lot about you. They want to know if you're a trustworthy person in the same way that you want to know if they're trustworthy and they'll go do good work. So it's a strange bi-directional relationship that has a lot of interesting information if you can get at it. And I should say that neither myself nor any of my colleagues signed up to this website and intervened in the discussions. I think that would have been immoral or unethical. But it was interesting to see what people were talking about along the way. In terms of Kaleidoscope, like I said earlier, we had this open science collaboration, and we had this great community of really motivated early career scholars. In the end, we didn't get a good distribution across all of the globe. This is not because we didn't try, it's because we had a short amount of time in which to collect the data. And we wanted to make sure everyone had a reasonably equal chance to contribute to the process. In terms of the images that you're working with in multimodal data, or perhaps videos, I think that there are many important issues here, and they're becoming more important over time. So are you working with photographs or non-photographic visual data? From which sources are you collecting these? Are they web scrapes? Are they curated? Or are they private data? How are you licensing your data? This is something that's becoming extremely important. I learned a trick recently. I don't know if this trick will always work into the future. If you don't want a corporation to work with your data set, slap on Creative Commons non-commercial licensing. You can't take it back. And it turns out that corporations are very reluctant to even evaluate on data marked as non-commercial. On the other hand, if you want big tech companies to use your resources when they talk about the performance of their flagship models, then you should probably allow that. Another really important issue is how are you protecting PII? This is really crucial from an EU perspective. And things like the GDPR and the AI Act have very long arms. So in a recent project we're working on, we have developed some tools into our data collection processes to blur people's faces. We don't entirely know if this is enough in terms of the AI Act and the GDPR. I feel like most issues around that are about legal testing instead of knowing for sure in advance. But we're trying to do our best by this. In terms of private images, in Foodie QA, we asked people to upload images of Chinese food through a survey published on Tencent. And we asked them to upload the image, to select the type of cuisine, to tell us about the dish name from their opinion, whether this dish was cooked at home, eaten in a restaurant, eaten in a canteen, or it was delivered, and to confirm that the photo had not been uploaded to any social media platforms. We did this because I had this really strong suspicion that vision and language models would perform better just by working with images they had seen before. And this turned out to be true for the models we evaluated in 2024. In the light blue lines here, we have the model being tested on our private collection of images. And in the dark blue, we have the models being tested on the publicly available images that are good enough replacements for the examples that we have. And we can see for QuenVL, for Idifix2, and for EVL, there's a big difference in performance when the model has seen that type of image, or it's likely to have seen it, because we don't exactly know what models like Quen and E are trained on. In terms of Kaleidoscope, the images are not really photographs. There's not a huge proportion of those in there. But with Kaleidoscope, because we have in-language exams, we can test model performance in many different ways. So we can see how well models perform on diagrams or figure understanding or formula understanding or maps. And I think this is a really cool way of trying to understand what are the different strengths and weaknesses of vision and language models. And here we are benchmarking Gemini Pro, Claude 3.5 Sonnet, GPT-4o, and Quen 2.5, 72 billion, because these were the best performing models. But we also looked at many other types of models and scales, going all the way down, I think, to 3 billion parameters. And I think that these types of resources not only help us understand vision and language modeling in general, but also how we can perform better for different languages. Speaking of language, when you're working with vision language datasets, there's always a notion of what type of text do you have. Is it questions that you have in your text? So Kaleidoscope has questions, Marvel has questions. Or are they sentences like in Lion or XM3600 or Multi30K? And then there's also a question of what types of languages are these? Are they natural? Are they produced for something that has nothing to do with your task? Are they programmatically generated? We were able to do this in 3D QA because we had spent a lot of time defining a taxonomy. Or are these crowdsourced by people that you pay? So in Kaleidoscope, like I said, we had a collection of really motivated volunteers. The texts in Kaleidoscope were not written by anyone involved in the project. They were created by exam board professionals for educational purposes. And we cover something between 14 to 18 languages. And we try to have a good distribution between multimodal and text-only samples. And here's an example on the right-hand side in English, which is a real example from our dataset. And I chose it for the summer school because I thought everybody probably knows what a finite state machine is in this room. And this is actually quite a reasonable question to encounter in a computer science exam. One thing I want to highlight here about the languages is that unlike other projects that you might see, we actually did this English last instead of English first. So we were reaching the last couple of days of collecting the data, and through Discord discussions, we realized we had every language except for English, and we probably should fix that. And that was quite easy for us, whereas some of the languages were a bit more difficult to collect along the way. And in terms of 3D QA, like I said, because we have this taxonomy, we were able to create templates and to fill in different types of attributes of dishes into the questions so that, for example, we could say which region of this food is a speciality. Because we know what's annotated for this, we can programmatically generate that to create single image QA examples. This is something that's really challenging for models. It's actually quite easy for Chinese native speakers. We also have an English speaker example in the paper. That was me. Single image QA is super hard for me because I don't know anything at all. Whereas multi-image question answering, where you usually have to figure out what's the contrasting example, was much easier. And so I think procedural single image QA examples are quite an interesting direction to go, but it takes a lot of time and energy to create these data sets. The final thing here is about the binding between the language and the visual modalities. And so the content that's expressed in textual data depends on its purpose. I think that many people in the room know who this woman is, or maybe she's so far out of the world now that nobody remembers who she is, but she's very important. And if you ask people on Mechanical Turk to write a sentence about this, they will say something like, "A woman in a grey suit is giving a speech." And it's not wrong. It's a good description of the image. And that's what I would call strongly bound multimodal data, where you can identify exactly where the woman is, you can localize the suit that she's wearing, and you can highlight maybe the lectern at the front with the microphones to signify that she's giving a speech. The only thing that's not described is the background behind her, which doesn't seem interesting. Maybe the fact that she's wearing a necklace or that she has a glass of water near her. The sentence that appeared alongside this image in the world also doesn't mention the name of this person. It talks about how social media platforms often form echo chambers. I mean, it's crazy how much this stuff has been discussed over time. I think this example is very old now. And Angela Merkel was giving a talk about how this was a problem back when she was still Chancellor of Germany. And so this is what I would call weakly bound multimodal data. It exists on the web naturally, but this image and text pair are supporting a newspaper article. And so it's forming a much broader narrative. And the narrative within that newspaper article will mention this person by name. It will say that Angela Merkel gave a speech at a conference. But harvesting this data from the web won't give you that directly. And what has been found is that if we take this type of web scraped data on the left-hand side and we rewrite it using image captioning models, we can actually train much better multimodal models from it. But I think that's because we have quite a narrow scope of the multimodal tasks that we have been interested in. And I think that as we go forward and we work with things like in-language exam datasets or fine-grained Chinese food understanding, it's going to be more important to try to work more with the naturally occurring mind data from the internet. So if we apply some of these different perspectives to datasets that are commonly used and seen in the literature, we have the COCO dataset, which is typically used for image captioning, or you could use it for retrieval. It's a data set of images covering 80 common objects in context with human-authored captions. It has object segmentation data. And so we can see that the people who actually created this, they were crowdsourced, they were paid for it, they were given tools to annotate the bounding boxes around all of these sheep. Obviously, someone gave up along the way because I can see loads of sheep in the background that don't have bounding boxes on them. And that's exactly what happens when you crowdsource. You think, I must be finished by now. I'm only being paid 5 cents for this, and I need to move on. There's a data set like conceptual captions, which was released by Google in 2018. This is previously has been used for pre-training vision language models, where they had a collection of normalized English captions, where you would go from the original alt text through a sequence of normalization steps in a pipeline, so you could transform from something like Demi Lovato wearing a black Esther Abner Spring 2018 gown and so on, into pop rock artist wearing a black gown and sandals at award ceremony. The thing on the left is this kind of weakly bound multimodal data that's hard to learn from. Whereas on the right, it's much easier because you're going to have more frequently occurring tokens that the model can actually understand. And it was released using a collection of URLs. This is how the researchers managed to get around the problem of copyright. But there's a lot of problem with link rot over time. And so I think most of the data has now disappeared due to images being shuffled around or domains changing hands. And so this is why we then get data sets like Lion, where they're really massive and quite stable over time. There's the VQA dataset, which is a collection of 1 million image question pairs. So this is also data that's crowdsourced, that has a very specific goal in mind to understand the kind of multimodal knowledge understanding of models. People were paid for this. All of this textual data is questions. The images were carefully selected so that you could have balanced pairs to avoid shortcut learning and easy answers. The visual common reasoning dataset has hundreds of thousands of multiple choice question answer pairs derived from movies. So that's a source of copyrighted data. And in addition to also answering questions, this I think was one of the early examples of tasks where you had to provide rationales for why an answer was correct. It wasn't enough just to produce the expected output. As a completely different type of data set, I'm super excited about sign language processing. I think it's a type of vision language learning where not many people have done much work in this area. But this BBC University of Oxford dataset is cool. It's thousands of hours of signed videos covering many different domains. And it's been used for sign spotting and sentence localization. But I think that there's also some real scope to do some exciting work further in that direction. Like I mentioned earlier, there's MMMU Pro, which is English multimodal questions from college exams, quizzes, and textbooks, which were collected by university students from online resources, trying to adhere to copyright restrictions. And there's also some really interesting work that's been done within this kind of context. And finally, Vision Arena is one of the newer instances of vision language datasets. So I guess everyone has heard of LM Arena, and Vision Arena is an extension of that, where instead of having language models battle against each other, you can have vision language models do it. And they have publicly shared a diverse multilingual data set of almost 250,000 human conversations with VLMs. So we have such an interesting diversity here. We have Russian, Vietnamese, and Chinese as the most frequently used languages for interaction. Then Korean, Japanese, Bulgarian, German, French, Portuguese, Persian, Italian. There's a huge diversity here in the data that we have. And it covers quite a large distribution of input image types and questions. And they were able to use 100,000 samples of this to achieve almost the same performance as the Llama 3.2 11B Vision Instruct model trained by Meta. And it's quite clear to most of us that Meta trained their model on way more data than 100,000 samples. So I think that and it took 2 days on A100s to do this training, which I think is within the reach of all of us. So I feel really promising and hopeful about this type of direction into the future. And there are many, many more examples of data sets and tasks. We could talk about this forever. But I think there's also this effect of ethical issues. So these multimodal data sets are being increasingly scraped from the web with unknown degrees of conformance or even any information about how they're being licensed. There's about 2.5 billion Creative Commons licensed objects online in 2022. That's the most recent information I can find from the state of the commons. Maybe this has been updated more recently, but there should be enough data out there for us to train without being too ethically compromised in terms of our research. But I think that with this idea of scraping data from the web, there's also this problem that we get into, which is scale first thinking. Question.
Meaning that the sources.
Yes, so the question is whether the 2.5 billion Creative Commons licensed objects have been cataloged. The answer is yes. And I think maybe something like 500 million of them are just scientific artifacts, like models or the outputs of experiments. The rest of them are things like web pages or photographs or videos or other types of multimedia data.
Where is this catalog?
It's available in the appendix of the Creative Commons report from 2022. So I think that they have some kind of internal catalog that they keep.
Okay, so it's not publicly available?
I would need to double check to find out if it's publicly available.
Okay, because I guess a catalog about publicly available data not being public, is that kind of...
Yeah, you get into a horrible cycle. That's a good point. And it would make sense that someone at the Creative Commons Foundation would like to know how much data is licensed. Yeah. Okay. So, yes, scale first thinking is great, except when it causes problems and it perpetuates harmful stereotypes. So, Abeba Berhane and colleagues in 2021 showed that systems like CLIP are good at perpetuating harmful stereotypes. This is an example where we have Eileen Collins, the first female American astronaut. And if you ask Clip which sentence is the best description of this photograph, it's the one that stereotypes her as a housewife in an orange jumpsuit, instead of the one that actually explains who's the person in the image, an astronaut with an American flag in the background. And so I think that there's still a long, long way to go when we're trying to build vision and language multimodal systems that represent a good distribution about the world. And so this leads me onto the first reflection I have on a research project that we worked on in Copenhagen about how can we collect multimodal data that actually better reflects the diversity of the world. And this was a project we presented at EMNOP in 2021, based on the understanding that most vision language data is in English or some Indo-European languages. And most of the images that people work with in vision language learning are collected from ImageNet or COCO, which reflect North American or European visual cultures, which gives us a really narrow domain over which we can make claims about how these models perform. Like I've said already in the first part, we have data from ImageNet, which is derived from the English WordNet hierarchy, or COCO, where these are 80 types of commonly occurring objects in North American contexts. And so we took the perspective that some concepts are going to be most better and immediately understood within a cultural background. And so I have these three examples of images here. And for those of you who didn't download the slides, does anybody know which concept is shown in the image on the left? Is anyone from the Basque country or Indonesia? It's called Pilota or Jai Alai. Most of you probably understood that this was a game, a sport of some type. If you don't know about this sport, it's quite terrifying. These two women are engaged in a sporting activity where they have some kind of weird bucket attached to their hand, and they throw a really hard ball at a wall at about 150 miles an hour, and then try to catch it again in the bucket and throw it back at the wall. I don't know why anyone would play this. It seems really dangerous, but I think it's quite popular in different parts of the world. For the second image, does anybody know what this is? No? Could we agree it's a musical instrument? Do we have that kind of basic level understanding of concepts? I think so. It turns out it's a sanshan or a shamisen, depending on who you speak to. It's a specific type of musical instrument that I think has 3 or 4 strings. And the example on the right-hand side, I wouldn't expect anyone to get this, because this is something that happens 5 or 6 miles away from my hometown in the north of Scotland, where it's a great honor to be invited to carry, to be involved in carrying a massive barrel of burning tar around the city to celebrate the new year. It seems extremely dangerous as well. I don't think I would ever want to receive the honor and privilege of doing this. But from a basic level, we could understand it's some kind of group of people, and it looks like they're on fire. And There's been a lot of research and philosophy on understanding concepts and hierarchies going back to Aristotle. And one of the things that we know from more modern philosophies in this area is that categories form a hierarchy. I'm particularly fond of the work of Eleanor Roche, thinking about how we have basic level categories, superordinate categories, and subordinate categories. And for the concepts on the previous slide, we really struggled to get to the subordinate categories, but we were able to understand them at the basic level because we knew which words we could combine together. And in terms of thinking about concepts and categories, there is a familiarity of individuals effect, which is what we're trying to get at when we speak about the idea of considering cultures across the world and not just assuming that ImageNet and WordNet is the right place to work from. If we actually take ImageNet or COCO or Visual Genome as our data set to understand how cross-cultural or cross-lingual they are, we can use Wikipedia to estimate this by taking a SYN set from ImageNet and looking up, does it have a page in English, and then finding links into other languages on Wikipedia. And if we do this over all of the 1,000 classes, then we can find that most concepts appear in 30 or fewer languages. So they're not very well distributed. And there are very few universal concepts. So here you have things like person or bed or dog or food. And so what we tried to do here was to create a data set for vision and language reasoning that was representative of the cultures of annotators across 5 diverse and independent languages, where we have culture-specific annotations from Indonesian, Swahili speakers, Turkish, Mandarin Chinese, and Tamil speakers. And this was for a task of visual reasoning where we had a data point with 2 images paired with a sentence. Are there any Tamil speakers in the audience today? Yes, there's one. So we don't actually have an English translation of this. I hope it's good Tamil. I think that somebody did quality check it, but please tell me later if it's terrible Tamil, because that would be embarrassing and I don't want you to tell me now. Um, So this is sentence paired with 2 images on the left, and the model has to predict whether this sentence is a true description of the pair of images. We did this in a native speaker-driven protocol from start to finish, and we created it from what we call universal concepts. So this is where we introduce a bias into the process. And when you create data sets, you introduce biases at some stage, no matter what you do. It's unavoidable. Here, we worked with the Intercontinental Dictionary series, and we focused on the chapters that were about concrete objects or concrete events. In terms of the data collection, we asked native speakers of languages to start from a semantic field in the dictionary, for example, sport, and then find a Wikipedia article that describes that sport in their language. And that's the second major bias we introduced. We wanted to have a Wikipedia article because eventually we had this idea that we could encode the Wikipedia articles into the vision language model, and this would improve performance. But this was way before in-context learning was happening, and so we had these ideas, but we didn't know how to do it, and we haven't come back to it yet. And then we extracted the top 5 per semantic field, and across the 5 languages, we got about 90 concepts from this crowd working process. And between 10 to 25% of these concepts couldn't be found anywhere in the English WordNet hierarchy. So we felt confident that we were going to get examples that already went beyond what was being tested in common vision language datasets. For the image collection, once again, we worked with native speakers. We wanted examples of images that contained one or more instances of a concept, or maybe the concept was interacting with other objects, or maybe it was being used to perform an activity, or it was displayed with a diverse set of features. And once we collected this data, we then performed language annotation by matching image pairs at random and having a native speaker write a caption being true for only 2 of the pairs, and then having someone validate this annotation. If it was not good, it would go back. If it was good, it stayed into our dataset for a final annotation. And the inter-annotator agreement on this was really high. We got a Fleiss kappa of 93%. So the final output here gives us a good bound on what models could expect to perform on this. In terms of what this data actually looks like at the end, here's an example from Turkish. The gloss reads that in one of these images, there are multiple people with kanons on their knees. Does anybody know anything about kanons? Did I even pronounce this word correctly? If I didn't, please tell me. This person here. Kanon. What do you think about this question? Is it true or false? It's a statement, so which would this be true statement or a false statement? And so in that case, if the statement is that in one of these images there's multiple people, then the answer is yes.
Yes.
Because it describes the image on the right and it's contrasted to the image on the left.
Yes.
Yes.
Correct.
Perfect. So that's I guess this is a type of musical instrument. I have no idea what it sounds like, but it seems like you have to play it by resting it on your knees. Could you rest it on a table?
I have never played that instrument,
Hmm.
but most of the time they are putting on their own body,
Okay.
on the legs.
Okay, thank you. There is a version with a table. Okay. So the second example here we have is a Zumari. Are there any Swahili speakers? No, not today. So the statement is that in the picture on the left, there's just one person blowing a flute, and in the picture on the right, there are two people blowing a flute. And the only way this can be correct is if the sentence is true. It actually is. This is a type of flute. I recently gave this exact lecture in Rwanda last week, and the person had never even seen this type of flute before. And so, because Swahili is a country spoken in many different languages, it turns out that our data was even more fine-grained than we had imagined at the start. So we have this data set, and we want to know whether vision and language models can actually understand this type of multilingual, multicultural data. As a sanity check, we trained a vision language model ourselves. This was back in 2021, based on an MBERT language model or an XLM Roberta language model. And it performed reasonably similar to state-of-the-art English models at the time. So we felt quite confident about the model we had built. And then when we went to test it zero shot on our new multilingual, multicultural data, it was absolutely devastating. The models dropped to nearly 50% accuracy for every language, and it's a binary classification task. So there's no clear demonstration of multicultural visual and language understanding in these models. And so coming back to what I mentioned earlier in the talk about multimodal binding, we had this intuition that maybe our low zero shot results were caused by poor binding in different languages because we'd only pre-trained it on English image and text data, not in multilingual image and text data. So we did the most obvious thing, which was we machine translated a lot of text using the M2M 100 model. And we had to throw out a huge amount of the text that this produced because for some languages, the machine translation model was terrible and it would produce never-ending repetitions of tokens. And what we found in the green bar here is that doing cross-modal, multilingual, multimodal pre-training helped a lot. And this is a strategy that's now employed in almost all multilingual vision language models because it's so useful to gain performance. I think the state of the art in this area is a model called Centurio. This is a model that's initialized from Qwen 2.5 and the SIGLIP image encoder. And it's trained on 5 different tiers of languages with a distribution that's 50% English and 50% multilingual. And it also has a really strong focus on multilingual text and images for OCR. So there's a lot of naturally occurring data and a lot of synthetic data from OCR and machine translation. And if we look at the Marvel dataset as an example through time, we've seen steady improvements on zero-shot performance in this task, going from 54.5% back in 2021, all the way up to 81.7% as of the ACL conference on Sunday, this coming Sunday. And the things that are driving performance benefits and improvements in this area is a combination of better visual encoders, better language models, better techniques for training the bridge between these, and machine translated and synthetic data. Because even with resources like Lion, it can be really hard to get high quality data in different languages along the way. We're about to start the second part of this talk. Are there any questions before I continue? There's a question here at the side.
Hello, good morning. Thank you for the great talk. I have a question. Maybe I have missed this point on the multilinguality. When data set of multilingual is decided to be annotated, how do you choose the languages? For multimodal, I think it could be based on the image. So if the image is from different culture, I think that could be one approach. And rather than that, if that's not the case, how would you choose languages? Because there are so many languages, and to always look for the rich resource and not to go to the other resource languages, how does it go? Thank you very much for that.
Can you hear me? This is a great question, and it's something that we talk about all the time. We deliberately try to choose languages that will be linguistically diverse and also physically, geographically diverse across the globe. We also try to work with lower resource languages where possible. Higher resource languages are, in my opinion, not so interesting from a research perspective because there's so much monolingual data out there that a good vision language model can be expected to perform quite well in a high resource language. In terms of how we actually get access to lower resource speakers, we've taken different strategies across the years. So we worked on the Prolific platform for Marvel, and there you can specify the language skills of different people. For Foodie QA, we had a collection of Chinese expert speakers who could also get us to different regions of China. Whereas for something like Kaleidoscope, we leaned really heavily on this 5,000 person open science community that Cohere has built through Discord, where everyone was welcome to contribute to the project. And there's such a diversity and breadth of different language skills within that community. So I think there's no one size fits all, but the people are out there if you can try to find out how to access them.
Hello, thank you so much for the talk. And I am actually doing speech processing, and I know maybe my question about the data is not immediately equivalent with big data in vision and language modeling, but I am very confused by the how to define high quality data today. So there are many papers demonstrating maybe clean data is the best. Noisy data will also help, and probably like more diversity in data will be good. So I was wondering, from your experience, what will define high quality? And if we want to generate some data, make some synthetic data, what would you recommend to do?
Thanks for the question. I won't answer it with a focus on speech processing because I'm not an expert in this area, but this is such a hard problem. We actually recently finished working on a project for synthetic data generation for fine-tuning language models, and we couldn't find any metric of data quality that would explain the final performance of a model we fine-tuned using different techniques for synthetically generating data. And the student that led this project went to a workshop at NeurIPS last year on fine-tuning language models and spoke to a lot of people from many different companies about this. And it seems like the general strategy is synthesize it and train on it and see how well it performs. I know that that's not a good answer and it doesn't give you much hope. But I think that in many instances, especially if you have a really small amount of data, then a decent process for producing synthetic data is going to be quite useful because you have too few examples to learn something useful. And by a small amount of data, I'm going to take inspiration from a colleague on one of my former projects, Jonas Pfeiffer. He defines a small language as one where its Wikipedia would fit on a floppy disk. And that's a really, really small amount of data. So if you have more than that, you're not yet in the really low resource setting.
Yeah, thank you so much.
Thank you.
Thank you for the great talk so far. At the beginning of this presentation, there was this slide in which there was written that we don't have new ideas in AI, but we have only new data sets. So I somewhat agree with this assessment. Do you think there is something that we need to change in the way we conduct research? I mean, in terms of approach, mentality, paradigm. Do you think that we are reaching a point for which we are going to get stuck on what we do? I mean, I would like to know your opinion about this in general. Thank you so much.
I think that's a really good question. And I think the answer is yes. And I would refer you to a paper that Sarah Hooker wrote last year about the bitter lesson of the bitter lesson, where the predominant belief in machine learning is that scale is all you need. And Sarah made a very convincing argument that this is probably not the correct way forward. I may be misquoting her, so I'm looking to see if I have misunderstood the main outcome. She thinks it's okay. So yeah, I would highly encourage you to read this paper as a different perspective on where we should go.
Can you repeat the name of the paper?
No, because I don't really know
Okay,
it.
maybe I should ask later.
What's the paper called? Sarah says she will talk about it this evening, so I think you'll get the...
Thank you.
Okay, I think we can get back to the lecture now. Thanks for the good questions. In the second part of this lecture, we're going to talk about data representation, and then we are going to rush to coffee to recaffeinate and fill ourselves up with carbohydrates and sugars. So I think there are three basic levels of representation that we use or can use in vision language models. Perceptual representations, pre-processed features, or raw inputs directly. Perceptual norms are a really old school approach to asking people to describe the properties of objects. Ken McRae and colleagues asked people to write down the words that were triggered in them by a textual stimuli. So here's an example of the top words that were triggered by the word moose. For example, that it's large, or it has antlers, or it has legs. And they also classified the type of knowledge that was needed for a human being to produce this output. So for example, to say that a moose is large, you need to have visual form and surface knowledge. Whereas to say that a moose is hunted by people, you need to have functional knowledge of things in the world. Whereas the fact that a moose is a herbivore is taxonomic knowledge that you get, for example, by reading Wikipedia, or maybe even a dictionary, but I think Wikipedia. And they collected this over 541 noun concepts. At the time, this was a large-scale data collection, but now it's a lot smaller in its scale, but it was very influential. And in terms of some pros and cons of this, seems like it's quite a simple task, and you get rich features out of it, but it's hard for it to scale. And I also think that it leads into a more deep philosophical question of what does it mean to understand symbols if you can only define them in terms of other symbols? And maybe some of you have taken more philosophy of computer science classes at university, where you've read about John Searle's Chinese room argument. And I think that this is where perceptual norms really kind of push at the limits of what we can expect from our models. In terms of going beyond these perceptual norms, the earliest work in the neural network era used either pooled features or spatially preserving features from convolutional neural nets. This is an example image of a historical artifact called AlexNet, which was extremely important in the development of deep learning. And so when people worked with AlexNet to extract visual features, they either took spatial features or pooled features. If you ever read a paper from something like 2015, you would see people talking about pooled features as being 4,096 dimensional activations of the fully connected layer immediately before the classifier into the 1,000-way ImageNet categorization task. Whereas papers working on spatial features would talk about how in our experiments we use a feature map, and this would come from one of the different layers inside the convolutional stack. If you go beyond vision and language models, for example, if you wanted to do object segmentation, you would find approaches that would use these spatial features at different convolution layers in the model, getting really fine-grained information up to more coarser information to find the boundaries of objects in the image. Then there was a shift to working with pre-processed visual features that were based on object proposals. And so this was called faster RCNN. This was a model that was trained on the visual genome dataset, and it had a region proposal network. And so what would happen is you would process the image with a CNN. The region proposal network would suggest where regions of interest might be. Those often co-occurred with being objects. And then you would re-encode those proposals with the CNN to give you a single dense vector representation of that part of the image. And people would usually work with maybe something like 36 regions of interest or maybe 100 regions of interest extracted from these types of models. And this was where the actual ResNet backbone came in at the bottom with its 101 layers of depth. And this was a longly established practice, but which was usually an offline process. You did it once, and then you didn't have to do it again, but you created really, really large data sets in the terabytes, and you had to use process tools like H5 to store this. And it was not obvious how to augment the data when you were working with this because you had already extracted the visual representations from the model. And there was a lot of specialist knowledge here in terms of installing packages like Café, which was a real pain in the ass. And so every time you feel frustrated by Hugging Face, know that in the past it was a lot harder to get things done. Nowadays, what we see is people working from raw inputs directly using a vision transformer. And so you take the input image, and Shweta spoke about this a few days ago. This is patchified, so turned into a sequence of patches, which are then projected into a transformer encoder, which is trained to classify the type of image. And since you have attended the lecture on transformers, you are already experts on how this works. The main difference is that the vision transformer added an extra pre-normalization layer before the multi-head self-attention block. And this pre-normalization layer is now used all throughout language models as well. And so it turns out that it's really helpful to add this into our transformer stacks. You can also have some fun in trying to understand what on earth these cryptic model names could mean. We think that we have it bad for language models. What on earth is a VIP B32384? Good question. Usually the start is going to tell you about the model family that you're working with. So this would be similar to something like Llama 3. Then you have the model size, and this has been somewhat more unified across vision models than language models. You also have the patch size. So when you split the image into patches, are they going to be 32 pixels by 32 pixels or all the way down to 14 by 14? And then you have information about the image size the model is going to work with. So sometimes it will be 224 squared or 448 squared, and you can just keep going up if you have the GPU RAM to do this. And there's an important interaction here where the number of patch embeddings you get is a function of the image size factored into the patch size. And so if you want to integrate a vision model into your language model, you have to be careful about the type of inputs you're working with. If you want to use the huge model, which works with 448 by 448 and uses a 14 by 14 patch size, you now have 1,000 patches as the input. And if you have a 12 input question, it's obviously really hard for a vision language model to distinguish which parts of the inputs are going to be interesting and relevant. In terms of how you extract data from VITs, you can, once again, just like we saw for ConvNets, work with using pooled features, from example, the CLS representation, or patch level features. And this is really similar to taking the spatial features from inside a ConvNet. There's also been some advances here on trying to work with higher resolution images. There's a paper from Coling 2025 on trying to combine local and global representations with frozen vision transformers and LLMs with a LoRa adapter to try to adapt the representations of the local and global features that you can extract. And you also don't always have to do this as a learned process. There was a similar paper from ECCV 2024 where without any additional training of the model, you could take the original representation, pass it through a vision transformer, upscale it to a larger version, do the same process as the previous slide and split it into smaller images, process those smaller images, and then merge all these features together, pull them down to the original size of your input and concatenate them together. Both of these approaches will give you better performance on understanding multimodal data that requires finer grained understanding. And this kind of makes sense to me. It's a really good approach for both ideas. And one thing I really like about this is that you're not really increasing the complexity of the data you give into the transformer at the end. Sure, we have a 1500 dimension input that we need to linearly project into the model, but it's not as if we've gone from having 16 by 16 patches to 32 by 32. We know the problems of self-attention and its n-squared scaling properties. And so the main pros and cons we have here is that data augmentation is pretty straightforward when you have raw input because you can do rotations of the image data, you can manipulate the color channels, you can take random crops. And so you haven't done this kind of deterministic pre-processing and saving stage, so there's going to be fewer creeping errors in the process. But the cons of this is that you're going to have smaller batches because you need to now put a vision transformer on your GPU as well as your LLM, which I think is why we're seeing a trend towards working with smaller vision language models instead of the large beasts that you find in the literature these days. And like I've just said, there are potentially too many inputs for your model to deal with this effectively. So to wrap up the second part of this lecture before we have coffee, there are so many different options for how to represent multimodal inputs to models. You can do it from a language-oriented perspective using things like perceptual norms. And actually, I think it's really useful sometimes, you see this in the literature, to take visual input and rewrite it into text as well. Object-related representations were very useful in the kind of 2018 to 2022 period. I think they might come back because knowing exactly where something is in the image can be useful for a lot of tasks instead of relying on the transformer to learn it through massive data and gradient descent. And more recently, seeing this shift towards raw inputs, which I think is the currently favored approach, because if you have the time and the GPU capacity, you can also update the representations in the vision encoder, which lets you learn a lot more about the domain of data you're trying to adapt the model towards. And with that, it is 10:26. I hope that's a good enough time for a coffee break. Hopefully the coffee is ready. I don't know. And if it's not, then our arrival will beckon the coffee to come towards us. I think there's going to be some posters this morning next to... No, there's no posters. They're all done. Damn it. I wanted to see some posters. Anyway, let's get some coffee, have some chat, and then we'll be back here for 11 a.m. Hello, everyone. Welcome back after the break. I can hear the excitement and enthusiasm of coffee and sugar flowing through the theater. We are approximately halfway through the morning's lecture, and I have reached slide 82 out of 165. So I think we're on time, but we'll speed things up towards the end if it's necessary. In this third part of the lecture, I'm going to speak about modeling techniques. And I've read a lot of papers on vision language modeling, and I am going to present a narrow view of the literature that suits an argument I want to develop. There are three different types of approaches in vision language modeling that you can mostly see as a thread throughout the literature. There are models based on cross-encoding, there are models based on cross-attention, and there are also models based on what we could call visual prefix learning. The cross-encoding models emerged as a key new modeling approach in 2019, where there were many concurrent papers on creating what were called visually grounded BERT models. And this was one of the earliest attempts at real learned model-based fusion. These models consisted of two components. There was a language encoder and a vision encoder, and then a stack of transformer layers that were trained to fuse these different features together in the representational space. The two earliest papers I know on this are Lexmert and Vilbert, but there is about 10 to 15 other papers with similar sounding names like VisualBERT, and they all try to solve the same types of problems. There were two main approaches to building these cross-encoding models. They were either based on single-stream or dual-stream architectures. In a single-stream architecture, the language inputs and the visual inputs were embedded using their modality-specific transformers, and then they were processed collectively using a single transformer stack with multi-head attention across all of the visual and language inputs at the same time. Whereas dual stream models tried to process the data somewhat independently by performing intramodal and intermodal self-attention operations. And so a common approach that you would see here would be something like K-transformer layers of modality-specific encoding, so only attending over the language inputs or only attending over the visual inputs independently of each other. And then having transformer layers where the queries would maybe come from the language modalities, but the keys and values would be transferring information from the visual modality into those representations, and vice versa. And this would immediately be followed by a modality-specific layer to try to kind of consolidate the information that was learned. A paper in 2021 showed that these were actually basically learning the same types of functions, and that their architectural decisions weren't having as significant an effect as people in the literature were claiming. Some examples of these models would be something like Vilbert, which I mentioned before. It was a dual stream model that was initialized from BERT, and it had these visual features extracted from regions of interest. This was using faster RCNN, which I mentioned just before the break. And they used between 10 to 36 regions of interest based on the confidence of the feature extractor. And they pre-trained this on the conceptual captions dataset with a masked language modeling task, which you learned about a few days ago in the Transformers lecture. Masked region classification, where for each of the regions of interest, the model tried to re-predict the probability distribution over the possible objects and things in that part of the image. And also an image text matching, which was inspired by the next sentence prediction task that Shweta mentioned on Wednesday. There was also a model called Vilt, which I think is really kind of at the start of the move towards working from raw pixels directly. Vilt was a single stream model that was initialized from BERT and took visual features directly from the vision transformer architecture idea. So the image was flattened into a sequence of patches, and then the modality was encoded in addition to the information about where the patch was in the image. And it was pre-trained on a collection of many different data sets for similar tasks to the Vilbert model. But one thing that was a real advantage of the Vilt architecture is that there was no pre-computed extraction of features, so it was much easier to work with new data sets, and it could better adapt to new data sets. One thing that was very important for them was they had to initialize their transformer encoder from BERT. If they tried to initialize it from a vision transformer, it did not work at all. And so I think that this is quite a common discussion that we see in the literature about whether vision and language are somewhat exchangeable representations. There are claims about the universality of transformers and how they can be interchanged. But for this specific problem of trying to learn multimodal representations, it was important to start from a language-based space and then fuse the visual features into it. In 2022, thank you, Facebook trained a model called Flava, which I think has some really nice innovations. So now you can see that the use of the patchified image had been solidified into the literature, but they trained a model where the image encoder had vision-specific tasks to solve during pre-training, and the text encoder had language-specific tasks so that you were retaining the properties of these individual modalities by themselves. And then the multimodal fusion layer above had multimodal tasks it was being trained on. And it's one of the few papers I've seen in the vision language space which actually retains evaluations of the original components of the model. I think more people should do that. And if you're thinking about doing vision and language modeling yourself, I encourage you to think about including this in your evaluations. It was also trained on what was the largest data set at the time of 70 million examples in the public multimodal data set. And so moving on from these cross-encoding models, we have dual encoding models, which are supposed to be a sample-efficient alternative to cross-encoding. And I think this is actually true because when you have a dual encoding model, you have two different towers. You have a language encoder and you have a vision encoder, and they don't learn cross-attention between their representations. So the most popular and well-known example of this is CLIP. And I think everybody here knows what CLIP is, so I won't labor this too much, but it's a 12-layer transformer for the language representation, either a VIT or a ResNet visual encoder. And you try to maximize the similarity of the embedded paired examples using a kind of NCE style objective. The thing is that it's actually really difficult to optimize this on smaller batch sizes when you have small compute power. So there have been some innovations in this area, for example, bring your own latent training, or innovations based on SIGLIP, which uses a sigmoid style objective. I think another thing that happened here with CLIP was when we really entered the period of not knowing much about the pre-training data sets that were being used. So this was a very large data set of an unclear provenance. There's a small paragraph in the paper that explains how they pre-trained it. And then eventually people tried to reproduce this in the Open CLIP initiative. And we also see this in the data comp challenge where they want people to train all of these open source CLIP alternatives. Moving on from this, we have cross-attention models, which are completely different from the ideas of the dual encoding strategy. And it tries to address one of the big problems with the cross encoding, because in cross attention, you assume you have a language model. And what you want to do is to make it aware of visual inputs. And you do this by adding cross attention layers into the model. The first example I know of this was Flamingo from NeurIPS 2022. And they did this by taking a frozen language model, a frozen visual model, and training these cross attention layers. And this has been a highly influential approach within the literature. But at the moment, we're seeing more and more people working with visual prefix learning. The first paper I saw in this direction was called Frozen. This was from NeurIPS 2021, where the researchers wanted to take a language model and then learn how to embed the representation of an image using just 2 visual outputs. That was all they allowed the model to have. And they trained everything to learn the vision encoder and the projection layer into the language model, which is, this paper from 2021 is basically all you need to know about where we are in 2025. So you're already experts after reading that one slide. A vision language model in 2025 has 3 major parts. You have these pre-trained components in the vision encoder and in the language model. And you usually freeze those since they are good representers of all the data they've seen. Then you define a connection layer between those models, and you train that connection using as much monolingual and multilingual multimodal data as you can find through continued pre-training and then instruction tuning and preference training. In the next few slides, I have some information about how these models are trained. And I'm using older models to explain this because for the newer models like Qwen3 and Intern VL 2.5, the details are becoming extremely difficult to find. Whereas back in early 2024, people were being a bit more clear about what they did. So we can see here for these first generation visual prefix VLMs, models like Lava and QuenVL and MM1 and PalyGemma, they were all using ideas based around vision transformers for their representations, either clip style models or SIGLIPs, and the language models were of completely different scales. So for example, we have Apple's MM1 with its small 1.3 billion parameter language model, up to Lava with its 13 billion parameter language model, making it quite difficult for us to do controlled and careful science to understand the different factors that are important along the way. In terms of the connector design, well, PalyGemma was an approach to try to map the image output embeddings from the vision transformer into the language model word embedding space directly using a simple linear projection layer and nothing else. And so this is also a follow-on from the ideas of the the Frozen paper from 2021. Whereas a model like QuenVL, at least the first iteration, tried to learn how to produce fewer output representations of the inputs. So you maybe give 256 inputs to the transformer encoder, but say, I only want you to give me 16 different outputs. And then the transformer encoder has to learn how to compress all of the visual input data into the output space. And then Apple, in their MM1 paper, argued for the importance of what they call a convolutional abstractor, where you have downsampling and upsampling of the original input patch space. But I think that what people are settling on now in the literature is this simple linear layer between the visual representations and the LLM representations. It's very easy to train. You don't need to add lots of complex nonlinearities into the space, and it can suit almost any type of data that you'd like to work with. There's a question here at the front.
So like this is very interesting, right? And I was wondering when it comes to like explainability, like if you're actually like just mapping into like embeddings that would be words as well, like, can you try to remap that like into proper real words and try to understand what it's actually doing, but by looking at the words that would sort of correspond to more or less, or?
Yeah, thanks for the question. So I think that Ellie Pavlik's group at Brown University has tried to do some work in this direction. I think her group has a line of papers at iClear and NeurIPS over the years. So that would be the best place to look for that type of information. But I think that there's no obvious reason to expect a guarantee that you will actually project correctly into the word embedding space, as you would align, for example, an image patch about a dog with the word dog. I don't think that actually happens. Thank you. And so back in early 2024, the training data sets we saw here, Lava was trained with about 600,000 image caption examples filtered from Creative Commons. And then we have the family of different commercial proprietary models, which are trained on billions of examples. In this case, Qwen was 1.4 billion examples split between English and Chinese. MM1 was 2+ billion examples, and Polygemma was a billion example mixture of multilingual image captions, VQA, and what they call in the wild datasets. I don't know how you get those, and Google wasn't very forthcoming about how one does, but I'm sure that a company that indexes the web knows where to find in the wild data. One thing that was really common about the data, the models from Qwen, MM1, and Polygemma, is they were also pre-trained on a lot of in-house data. So Polygemma used a data set called Weebly. I spent a lot of time trying to understand what Weebly is, and I really don't know. It's about 1 billion language image pairs that if you follow the citation chain through the papers, you don't become much clearer about how they collected it. If anyone works for Google, come and tell me. I won't tell anyone else. I will. I'll tell. If I'm invited next year, I'll tell everyone. Qwen VL was trained on 220 million examples of private in-house data, and MM1 from Apple was trained on 1 billion examples of in-house data as well. And these papers don't give many ablations so that we can understand the true benefit and value of all this in-house data. But we do know from training LLMs, for example, many of you might have seen these Hugging Face projects on FineWeb. It's really clear that careful filtering and deduplication can lead to much better language models. Exactly the same thing is going to apply to vision and language models. So once you've got your training data set, what's your strategy to success? The strategy that was being used in early 2024 still seems to be what people are using now. This is an example from QuenVL where they have different stages of training. So in stage 1, you freeze your language model, and then you adapt your vision representations in your vision transformer through some kind of connector layer. In this case, they had learnable query embeddings, but it could just be a linear layer projecting from the vision transformer into the language model space. And you're just using general image text pairs with low resolution images. Your main goal here is throughput on the GPUs. And then in stage 2, they would have what they call multitask pre-training in the visual space, where you now might unfreeze the language model because you want it to start learning about the properties of the domain of multimodal data you're working on. And in this case, you could also try increasing the resolution of the image data, because maybe you think, I want to work with medical images, or I want to be able to do really fine-grained recognition of small objects, or maybe OCR. And then in the final stage, you might use really high resolution data, and also maybe with something like chat interactions, where this was pre-vision arena, but this would be the stage where you maybe want to go straight for the supervised fine-tuning of the language model based on that. And that was what was so surprising to me about the Vision Arena paper. When I went to CVPR earlier this year, I spoke with the authors at the poster, and that performance that they got when they almost reached the level of Llama 3.2 vision was when they just did stage 3. And I thought, wow, that's super cool. I'd really like to try that myself and to understand how that works and whether it only works for kind of chat style evaluations or if it can work for many other types of tasks. Do we really need all of these stages, or are we going to be moving forwards to something new and exciting? And I think that there have been a lot of open questions about what we're doing here and how we're going to make this more accessible to other researchers. And so, how quickly can we realize some of the benefits that we see from larger scale VLMs into smaller models that we can run on our laptops or maybe on one GPU? Do we really need to have 1 billion examples to learn a bridge? Well, after talking to the people from Vision Arena, the answer is no. It seems like you can do it with 100,000 examples. But maybe with 1 billion examples, you develop a lot more robustness. And if you're trying to deploy a model to face customers on the internet, that could be something that's really important for you. And there's also a question of what will happen to model performance when we're starting to develop new tasks that have a lot weaker visual linguistic bindings. So things like visual question answering can probably be served really well by some of these strategies. But if you want to do in-language exam question answering in multilingual settings, maybe you do need richer models with larger visual representations. On the right-hand side here, I'm showing some examples from the PalyJama and the MM1 papers about the benefits of training your models with increasing resolution sizes. And as we learned just before the lunch break, increasing the resolution size and keeping the same patch size leads to massive number of visual inputs. So not everyone can get this average evaluation metric improvement of nearly 20 points. And also we can see here that pre-training for more steps gives much better performance. I think we know that already from LLMs, but we don't always have to compute to train for 200 million examples or 2 billion examples. Whereas on the bottom, we have this ablation study where the researchers showed that if you have resolution insensitive tasks shown on the right-hand side, it doesn't matter at which resolution you train your models. And that makes a lot of sense. Whereas if you want to eventually apply it to resolution sensitive tasks, it does make a lot of sense to try to rescale the data and use more compute power. But as we also heard from Baidi earlier this week, you get into this problem of the I/O between the GPU and your system is more constrained than the compute power you have on the system. And I think we'll also see an approach to how can we do something a lot more resolution sensitive, but while working with the GPU data directly. So I posed these questions last year, and they already got answered, a lot of them. So that was quite convenient. These trends will be realized in smaller models in less than 6 months. So maybe some of you have seen this small VLM set of models from Hugging Face. I think they're super cool. These are models that are specifically designed to be really small. So we have a graph down here showing the GPU RAM usage and performance on a set of tasks on the y-axis, and the smiley faces or the Hugging Face models going as small as just 256 million parameters. And this is a baby model, but it's really good if you can get this type of model and work with it and use it to do something interesting. Obviously, if you go up to 2.2 billion, which is the one at the top left, that's really good performance, and it performs better than models like PalyJama 3 billion, or even some models like QuenVL2, which is actually using much more GPU RAM to get maybe 5 or 6 percentage points more performance. And so what are the main findings that they have in this? One is about the importance of balancing the relative sizes of different components in your vision language model. So if you think about having a total budget for the size of your vision encoder and your language encoder, then, in your language model, in the blue bar here, we're showing if you have a 93 million parameter vision encoder, and you mix it with a really small language model, you're throwing away some performance. Whereas if you mix it with a larger language model and the total capacity is closer to 500 million, you can go from 30 to 40 points of performance on CIDR and VQA accuracy, which is a nice improvement. And this becomes even more clear when you're working with much larger vision models, So this is a 428 million parameter vision model shown in the orange bar. And if you pair this with a really small language model, your performance is terrible because you have, I guess, you have a mismatch between the representational capacity and also just what the model knows as a language model. If you pair it with the same size of language model as the language model that was successful for the small vision encoder, you get a nice boost in performance. But if you give it even more language model capacity, it keeps expanding in its capacity to work well. And I think this is a nice finding, and it's quite instructive for the type of work that you might want to do yourself. They also find that by giving more context length for the vision language model, you can get a really nice improvement in terms of the quality of the task performance. And you could imagine that this is because you can simply process more input examples, or you can maybe take advantage of chain of thought reasoning in the multimodal space, which is not so easy to do when you just have 2K context and you might be using something like 500 of those for the visual tokens alone. Whereas there is a diminishing return of massively increasing context length. But this is all still at the small language model scale. If we were working with really large models, like 13 or 30 or 200 billion, some of these results might be somewhat reversed. They also found that learned position embeddings are really useful and important. The orange bar here is showing what happens when you have a learned position embedding similar to what we would see in a language model like BERT. Whereas if you don't do that, and instead you use tokens to mark the positions of parts of the image, the performance is much worse. And I think this is where you get a kind of an interference between the language modeling space and the representational space of the visual inputs. And they also claim through some of their experiments about how using these so-called string locations, the loss trajectories of training is just completely plateaus for most of the optimization, which is a sign that something is going drastically wrong. And then it very quickly finds a way to solve the problem, but not in a way that was useful for you. They also found, and I thought this was really interesting, that chain of thought data in the language-only space hurts the model's performance a lot. They train these models to work with either video data or image data. And the more chain of thought data they add from their Smalltalk data set, the more performance decreases on their multimodal tasks. And I think this, for me, is a really important direction for future research here on trying to understand the interference that's happening between language-based tasks in a kind of conversational chain of thought style and multimodal tasks. I would love to see more work in this area, and I think that this is an important topic to focus on in the coming years. So the summary of this third part of the lecture, I have tried to cover the three main types of representation learning I see in vision language today. The cross-encoding approach is mostly fading out now because it's quite computationally expensive, but there were so many advances that were enabled by this. And we also saw this as the first shift from working with regions of interest extracted from images towards working with vision transformers directly as inputs. Then we moved on to, well, simultaneously, actually, we had a dual encoding strategy. And this is models like CLIP, where these are still commonly used on a nearly daily basis. Maybe some of you are using CLIP in some of your projects because it's open source and it's freely available for you to use. No, I'll call it open weight, not open source. And finally, we've seen this shift in more recent years, maybe since late 2023 onwards, to visual prefix learning, where I think we're seeing the real benefits of trying to take what's already learned in a pre-trained language model and what's learned in a pre-trained vision model, and to try to fuse these two different things together to produce, hopefully, a best of both worlds type of model. I think there was a question. I saw someone has their hand up back here.
Thank you very much. It's very, very interesting, actually. Do you have an idea what is the architecture behind the new open AI language vision models? Do they use in same time, you think, autoregressive and diffusion models similarly?
Thank you for the question. I have absolutely no idea.
Thank you anyway.
I'm sorry. I mean, this is just the truth. Does anyone know? Nope.
But related to that, maybe it would be an interesting dive in if you can share your thoughts with respect to, well, if you see what a model can do you have or can you have any insights with respect to how it was trained, or at least some decisions at some point?
I wish Maxime was still here. For those of you who attended Maxime's talk last night, I think he would have a great perspective on this. I remember during my PhD, which was a very long time ago, I had a colleague who was trying to determine what types of data machine translation models were trained on by looking at their outputs, trying to figure out if you could trace this back through the data. And we know that the Allen Institute for AI has things like language model tracing, where you try to do this kind of attribution back to training data. But I think that the approach from the Allen Institute for AI relies on access to the model in a way that an API-based model wouldn't give us that. And I also have a pretty strong suspicion that if you use the API from a corporate model and they eventually figured out what you were trying to figure out, they might shut you down. And maybe you remember there was this paper about trying to no, actually, I don't remember the details of that. But there was a paper where people tried to reconstruct the possible support of the model through the output representation space by prompting the model thousands of times. So I think that if you could somehow break into the data center, I mean, that's actually a really easy way of doing it. If we could break into the data centers for OpenAI and Meta, like somehow disguise ourselves as technical support staff, and somehow know the root passwords to access the machines, then we could do a kind of exfiltration of the models, and then we would just need to find like 1,000 GPUs that we could simultaneously use to load them. I don't think we're going to get to that stage. I'm sorry. I really don't have the answer to the original question. Okay, we can move on. So there's a paper that came out today. I haven't read it yet.
It was just a coincidence. There's a paper by the group at Rice that's called many-shot regurgitation prompting, which kind of the title is self-explanatory. The idea is to try to make the model regurgitate verbatim pieces of the data of the training set.
I think that sounds
Look
like
it up.
absolutely the paper that you should share. I mean, we did have this project in Copenhagen once where we tried to find out whether large language models would willfully engage in copyright violation by reproducing children's books, given an input prompt. At least back in 2023, many of them were very willing to do so, to like reproduce sections of Harry Potter. So I do believe that that's one approach to trying to find out what's in them. And we didn't need to do it by few shot prompting. We would just put in the actual tokens of the books. So I want to reflect on some work that we did last year on image captioning, where we wanted to know for building an image captioning model whether you need to learn everything in weights or whether you can take advantage of in-context learning. And this was a language agnostic and parameter efficient language captioning model that we trained using retrieval augmentation. Somebody spoke about RAG at some point in this course. I don't remember. But RAG is a really nice approach for you want to try to combine the power of in-weights learning through gradient descent with context adaptation, giving retrieved examples. And the general approach here is you have a data store of facts or knowledge or information, and you want to figure out how can you combine the most relevant items from your data store with the given input example you have for your task. And the way that this might work for text is you might have a question like, where was Alan Turing born? You could give this directly into a question answering model and pray that it knows the correct answer. Or if your data store contains web pages or examples on Wikipedia, then you could probably find the information you need and guide the language model to producing the output answer that you would like it to produce. And the motivation for thinking about this in the multimodal space was that there's been this trend towards training bigger and bigger vision and language models until small VLM came along and made everything small again. And an alternative that we were seeing was that we could reuse backbones and train small projection layers. And the small projection layer kind of gives you a really constrained bottleneck. So we kind of wondered, could you use retrieved examples as a way to escape from this bottlenecking problem and give the language model many more clues about what to do? And so the student called it paella because it was a funky name and she really liked paella as a food. Important decisions there. And so, like I said, the standard approach for training VLMs, we had an image encoder, a language model, and a mapping network. And then given an image, we had a retrieval system that would look in a database of image captions in many different languages to try to find sentences that would describe this image so that the model wouldn't be relying just on its in-weights representation. And then we took the top K retrieved examples and filled these into a template which would guide the model to try to produce outputs. So we have a template that looks like this for English. We also had templates for Italian and Spanish and actually 36 different languages. And then we would train the mapping network through trying to predict the expected translation, or in this case, in-language caption on the other side. Our retrieval system was based on a FAISS data store where we stored high-dimensional vectors, and the captions of the images were based on clip embeddings. And we tried to retrieve those k-nearest neighbors of the captions, not of the multimodal data, just the captions directly, obviously without retrieving the captions of the target images we were working on. And we trained a cross-attention mechanism, like I mentioned just a few minutes ago, where we wanted to, and so this is the transformer decoder, and we added in a new cross-attention layer that would attend over the visual inputs. And one of the observations that we had in this was that you wouldn't need a full rank projection of the visual inputs into the language model space. You could downsample it along the way to have fewer trainable parameters. And so if you worked at full rank here, you would have like 550 million trainable parameters over about 500,000 examples, which is obviously a pretty bad idea. And if you squeeze it down to just a rank of 8, then you could get down to as few as 34 million trainable parameters, which seems kind of like it's more the right ballpark. And these cross-attention layers are at every layer in the transformer decoder that we are merging all of this into, which at the time was the XGLM language model at the 3 billion parameter scale. And we used multilingual clip as the encoder of the visual data. And we trained it on only 500,000 image captions, sampled from 35 different languages that were machine translated from an English language dataset. And we evaluated it on a dataset called XM3600, which contains geographically diverse images in 36 different languages. And 5 of them are specifically low resource for Bengali, Kushko, Maori, Swahili, and Telugu. And when we look at the results here, I'm placing this in context of other models that are either trained on much more data, going from 19 million to 12 billion examples, or have many more trained parameters from 124 million up to 17 billion parameters. And so the Paella model performs really competitively against models trained with hundreds times more training data or up to 80 times more trained parameters. In particular, it also performs very strongly on these 5 low-resource languages, which I thought was a real success for the power of retrieval augmentation strategies. Because low-resource languages is something where it's quite hard to get a good distribution of this data, even at pre-training time. We also looked into whether this success was purely due to training it on 35 languages. So we have a variant where we trained it just on monolingual image data, English data, no data in any other language. And so you're just relying on the multilingual representations that the language model has learned. We did find that this reduced the performance of the model, especially for the low resource languages, but it's only 8 points worse. And so I think that this is performing much better than a model trained by some authors at Google on 35-way translated data. And so we're pretty much performing as well as that approach. But what they don't have is retrieval augmentation. And I think that shows the real contribution you get from giving this data just in time to the model. We also did some really careful ablation experiments to try to understand the value of retrieval augmentation in these strategies. And what we find, and these were the high resource languages in XM3600, the red bars are where you have no RAG in your system. And you can see that for a language like Hindi, the performance of the model is really bad without this. It doesn't know how to produce output sequences in Hindi. We also have an image blind system where the model just gets sentences as input instead of having the image. So you're just seeing, is this model just rewriting the sentences that you gave it? But if we also give the image as input, then the performance increases even further. And so I think that's a really nice demonstration of the relative contributions of different perspectives on multimodality and retrieval augmentation. And I actually hope in the coming years, people will look more into retrieval augmentation as a strategy, especially when you want to work with lower resource data. And this led us into another question, which was, do you even need to train models to do this? I've spoken a lot about this connection bridge that you have between different parts. We did a slightly insane experiment on this based on the idea of Socratic models. The idea behind Socratic models is, we can talk about the labeling of this, it's not great. Models are going to try to communicate with each other through output labels. And so the idea is that you might have an image as your input, and then you would take a vision language model to detect things in the image. And this would produce a sequence of labels that you could then communicate to a language model to generate captions based on a template. And this template reads, I'm an intelligent image captioning bot. This image is an image type. So it might be a photograph or a line drawing or painting. And then there are number of people. So that could be a person detector vision language model, and also a place detection language model and an object detecting language model. And then you have VLM produce many different captions by sampling through its output space. And then you can use a VLM to re-rank that against the original image. So the thing in the middle, the language model, which can be really expensive for decoding, doesn't actually need to attend over the visual data along the way. And you can end up producing captions that are, in some cases, quite reasonable descriptions of images, even though they've never seen the input image when producing the language tokens. I mean, this does actually come back to the thing I was talking about earlier about what does it mean to understand symbols that are only defined in terms of symbols. So John Searle's Chinese room keeps chasing us around this lecture, except in this case, the person that's feeding Chinese symbols into the room is looking at the image. In this case, they're a VLM. And the person doesn't have an English-Chinese dictionary for translation. They just have a set of rules on the wall about where they need to fill in different outputs. And so when we applied this to image captioning in a multilingual setting, we followed a really similar format for this. We have our image, we detect things, and we generate captions, and then we re-rank them. And we do all this by prompting a frozen language model with examples of how to work with this data. So in our case, we detect things by taking the image and finding nearest neighbor captions using a multilingual clip model. We generate captions using a prompt to the LLM, and then we re-rank using the multilingual clip model again. So we're continuously reusing components from this. We evaluate a range of models going from 500 million to 7 billion parameters, and there's no training or fine-tuning of anything anywhere here. The performance isn't great, but it's much better than you would think, and that was what I thought was quite interesting and surprising about this. Our model here was called LMCAP, and we can see that it performs quite competitively against models that are trained on millions or even hundreds of millions of examples in many different languages. And one thing that we found when we were experimenting with this is that you need a certain model size for this to even work. So if you look at the columns for Spanish, for Hindi, and also for simple Mandarin Chinese, there's a really big gap when you go from 500 million to 1 billion to 2.9 billion parameters. You need a certain amount of capacity in the model, either for them to be able to represent these languages well, or for them to be able to follow the instruction templates. We never got to the bottom of which of these two things was most important, but I think that there's some interesting thoughts about what you could do in that direction. And I'd also love to hear if you have any thoughts about how we would disentangle what's happening there. We also have some qualitative examples of this is the input image, and these are the retrieved captions using the multilingual clip model, retrieved in English. They all look quite good, actually. And the generated captions, so for English, 2 people and a kid skiing along a trail, that's really good. And I speak English, so I can verify that. Do we have any Spanish speakers in the room? We have 1. We have 3, 4. Is this okay? It's good? It's good enough for a model that didn't see the image? Are there any Mandarin Chinese speakers? Is this okay?
There's probably a gender bias that assumes that in this case is a boy.
There's always gender bias in language model systems. You can't escape it, right? Because there's no evidence in this image to say this is a boy or a girl. You cannot tell that. So that's just distributional statistics that we read out of the training data. But apart from the gender assumption, it's okay?
Oh, it's translation or
No, this is
captioning?
Chinese first.
So it's like generating caption for this image.
Yes.
Yeah, so it doesn't describe the whole sightseeing of the background. So it only says like skiing in the kind of like with snow, kind of a ground filled with snow. Doesn't describe the trees in the background. So it's like a little bit incomplete.
Yeah,
kind
so
of.
it's not giving as much data as the English one. Okay, interesting. Thank you for sharing that. There's a comment? Do you have a question?
If in this process that you discussed first, it's like a blind person that we want to ask him or her to send some information to another person, yeah? Something like this.
No, not
Because
quite.
the LLM can't see, the middle LLM can't see anything. We LLM should discuss something, and this LLM should process and then discuss it to the next one. So there's a problem here. For example, if we want to do a task that we need that trees, I should send back a feedback that I can understand. You should discuss a bit more, and then something like back propagation, but in a different way. So how can you solve this problem?
So I think some of your comments here are quite valid. I mean, I don't anthropomorphize it as if the model is blind, like a human. But I think one way that we could address this, and I've actually been thinking about this while preparing this talk, I think this is a really interesting application of agent-based frameworks where you could imagine having a system that would, first of all, you would ask it, what are the important things in the image? And then maybe you would collect those together and you could have an image sentence ranking model that would tell you how similar the sentence fragments are to the image. And then maybe you could have another round where you would say, is this everything that you need? Have you covered all of the important parts of the image? And only once the kind of verifier agent is satisfied, do you then go on to the next stage of trying to produce a sentence or to try to do some kind of recognition from it? I mean, I only thought about that yesterday, so I haven't worked out all the details, but I think it might be one way to do it without any training or gradient descent.
So in the zero shot setting, there is no valid solution there. For example,
I don't think there's a valid solution in a zero-shot setting because I don't think that the language model, the vision language model that's trying to detect things from the image is going to tell you everything you need to know.
for example, I want to as a middle LLM, I want to solve a math problem, and I asked the VLM to discuss everything about the numbers in the board. So then I asked it again, I need something more. Can you tell me again? And then if they have something like this conversation, they make something like this.
That might be a solution if you actually have a system in which people can interact with the model in more detail. But as a pure zero shot, like one attempt, I don't see an obvious strategy there. But thanks for the question. So yeah, this kind of wraps up the third part of the lecture on modeling strategies for vision language models and also some explanations of applications to it for multilingual image captioning. We're at 11:56 and we're kind of running low on time, and I don't want people to miss their lunch because we've all seen the queue. So are there any quick questions before we move on to section 4? Nope, they're all long questions. No, we can wait. So this fourth part of the lecture is about understanding multimodal models, which I think is really important, and it's going to become more important in the coming years, especially with multimodal models being deployed and more widely used in society. There are many questions we should be asking about going beyond task performance when making claims about our models. We should want to know what's driving the success of these models. Where do they fail? Where do they succeed? What types of skills do they have? Are they actually understanding linguistic structures, or are they just using bag of word type representations? And can we move beyond behavioral analyses to more model internal analyses? This was something that Maxime was discussing yesterday in his evening lecture. And I've tried to categorize what I've seen in the literature and what I think are interesting directions. So most of the work here starts back in 2017 on FOIL captions, where people wanted to understand whether vision and language models really understand the relationships between words and images. And so here they have an image of a pigeon or a bird next to some bicycles. And the FOIL caption is one where the pigeon is described as being a dog. And you want the model to demonstrate its language understanding to say it does not know what this is. And so these are crowdsourced data sets that contain plausible incorrect examples. And that's the really useful thing, because once the object that you're mixing in here becomes implausible, like a helicopter, it's going to be easy enough for a model to recognize that there couldn't really be a helicopter that close to some bicyclists with that kind of visual perspective. There's also been the vision and language understanding evaluation, where the researchers proposed a suite of 5 probing tasks to look for things like probing for visual relation information or visual coreference or the multimodal fusion degree inside of transformers, or maybe what type of linguistic knowledge they know or the modality importance. And one really interesting observation from this type of understanding approach was that back in 2020, the Unitar model was actually much more attentive to textual features throughout the model than visual features. And this is the type of thing that's not going to be apparent if you're just working on task success or task performance. The VALS benchmark from 2022 was about testing visual linguistic capabilities where there were small manipulations in the file pairs that related to things like existential quantifiers or counting or prepositional relationships, finding that it was really difficult for some models at the time to achieve good performance on this. But the model that performed best was a variant of Vilbert called 12-in-1, which was multitask pre-trained. And this is an argument that's been made repeatedly throughout the literature that pre-training on many different tasks gives your model actually fewer useful representations that can be accessible to all of those tasks. And so it ought to be better when you want to apply it to new problems or to new understanding scenarios. There was also the vision language checklist of trying to evaluate these models where you had manipulations to the data, not only in the language space, but also in the visual space. And so I think that this is actually a really cool application because we know how to do most manipulations to linguistic input data, but visual data is something where until we got really strong stable diffusion type models, it was hard to manipulate that data without breaking other artifacts in the scene. And so I think that this is also a nice direction for understanding models. Some research from Google tried to investigate something more specifically related to language, but also visual representations of space based on subject-verb-object probes. This is once again through crowdsourcing data and using foils. Foils just keep coming back all the time. And the Winnow Ground dataset was a collection of image text pairs to evaluate compositional understanding, where they had pairs of very near image text and text image examples where the model has to demonstrate some kind of more deeper understanding of how these two input modalities relate to each other. There's also been some work on understanding whether models are vision and language or vision for language. Some early results in this area suggested that these were vision for language models and that language modeling was still the thing that they really succeeded on, and that ablating different parts of the visual input caused more serious degradations to performance. And just a couple of months ago at CVPR, there was an interesting paper on trying to understand the linear projector layer that everyone is using. So this plot here is showing on the y-axis, so this is based on using a sparse autoencoder, which Maxime mentioned yesterday. And here, the orange bar shows if you give visual patch inputs to your LLM and you look at the reconstruction loss of the sparse autoencoder, it's really high at the early layers in the model. So in other words, it cannot reconstruct the representation that you gave into the sparse autoencoder from that data. And it's not until you reach maybe layer 20 or further in the pre-trained LLM that it does do a good job of reconstructing the representations. And so this leads me to question whether we have the right types of connector architectures if it's taking so long for the large language model and its sparse autoencoder to produce this representation. We recently worked on a project where we wanted to look at multimodal distributional semantics. And the main question we were thinking about here is how well do large-scale pre-trained language models represent semantic attributes of concepts? So those are things like roses are red, or they smell sweet, or a rose is a flower. So red is a really classic type of computer vision attribute that a vision model should be able to predict very easily. But the fact that a rose smells sweet is something we might expect to be easier learned from language. We know that humans are quite good at solving these types of tasks, but what we wanted to know is if you took a human and you kind of threw them away and replaced them with different types of pre-trained neural networks, where would their relative strengths and weaknesses come? And so we did this by training linear probes to predict these attributes, either based on visual representations of the data or sentences that described the concept. And this was framed as a hard generalization task because we only evaluated the linear probes on unseen concepts. So if the attribute was that something has 4 legs, the training set would not have an overlap with that. So it might be cats and cows and dogs, and then the test set would contain table. And the model would have to do some quite sophisticated reasoning, going from cats and cows and dogs to predicting that this wooden structure in an indoor setting would have 4 legs by looking at it. Our images were sourced from a dataset called Things, which was created by a collection of neuroscientists. So the images are very high quality and they really do a good job of focusing on the objects at hand. And we prompted the GPT-4o language model to extend the McRae dataset of perceptual norms. Now, I mentioned McRae about an hour ago, and it's really good because you have this human labeled data for perceptual norms, and we used GPT-4o to extend this out, and we asked whether a particular attribute was a common trait in the sense of a definition. And we didn't show it the images. We just wanted to work with the representation space it had of these concepts. And that cost about $90 to get all that data. And then we tried to extract visual representations using the average pool output of a vision transformer or modality-specific tokens inside the different transformer layers. In terms of the evaluation, we used F1 selectivity, which corrects for performance against a random baseline. And if we look here at the language-only approaches, we also included some old-school models like fast text and glove, and approaches like Gemma 2B or DiBerta, they perform much better. So there is something to be gained from contextualized representations of language for this. And if we look at vision-only approaches, the results really surprised us. So models like Swin v2 and Dino v2 perform quite close to the performance of Gemma 2B. And the thing about Swin v2 and Dino v2 is that they have pre-training without any label supervision at all. There's no language that's used to guide the representations here. And I still don't have an explanation for how this works. If you think you have one, please come and talk to me after the lecture. I will wait as long as it needs to talk to you about this. And then we also extracted the visual encoder from multimodal models like we've been discussing just in the previous section, and these perform better than either of the modality-specific approaches, which is kind of reassuring that we learn something useful about the world by combining visual and linguistic representations. And when we look at this from an attribute type analysis, because McRae did this for us, so we didn't make any of these attribute types up, we can see that taxonomic, so an is-a relationship, is the easiest for all of the different types of attributes, where the red ones, the red to orange, are more about the visual representations, and the green ones are more about the language model representations. Sound and taste are much better predicted by language-only representations, which kind of makes sense. I don't know how by looking at something you can detect its taste just from an image, unless there's maybe also a person in the image, and then you can learn something about visual reactions. And reassuringly, visual attributes are mostly better predicted by visual representations, like motion or form and surface. And that makes sense. That's a useful kind of reassuring finding. But not all of these findings align with our intuitions of what we would expect. What we do find is really strong within modality correlations. So the big block here at the top, these are all of the vision encoders, and they almost always agree with each other about what types of predictions should be made. And some of the language models almost always agree with each other about what types of predictions should be made. But outside of these blocks, we find that the language models and the vision models don't agree with each other with as much of a correlation, suggesting that they are actually learning different representations, but they're somehow able to make useful predictions about what they're finding in the world. And so I think this leads to an interesting question about whether these large-scale self-supersized vision models are maybe actually engaging in this convergence as suggested by the Platonic hypothesis, or maybe there's some kind of confounds and correlations that we're finding here in these results. I don't know what the answer is to this yet, but I think that this type of understanding of models in terms of how they're behaving is going to be an interesting direction in the coming years for vision and language model research. And I think we're also witnessing an interesting methodological shift here, going from just behavioral-based analyses to attention analyses, or maybe working with really careful data sets to probe what we're finding along the way. So I'm starting to reach the end of the lecture. In terms of some future directions, I still maintain, after many years, that physical understanding of the world is, I mean, we're almost there now in terms of it being something everybody wants to work on. So maybe some people here will leave the summer school and go and work on this. I think that predicting and explaining physical actions is going to be so important as we want to create embodied agents. And so this is something where, wait, no, I need to do it on this screen. I don't know how to play this video. I know how to click, but thank you. Yes, so this is not even complex real world data. This is pretty simple stuff with these smiley, googly eye objects. But some of the questions are really hard, like what was the color of the last object that collided with the tiny red circle? Does anyone even remember? No. I mean, could you even predict it from this state here? Because we know that humans engage in this type of forward prediction of the world. Which of these objects is going to collide last with the tiny red circle? I think some people are whispering, but the triangle. Sorry? This is the red one. Oh, I'm not pointing at the right thing. Oh, no, I am. Yeah, so somebody thinks it's the green triangle. It was the green triangle. Language models are not great at this. And you can probably imagine many reasons why. It's quite a difficult problem to try and solve along the way. So I think this is a super cool and exciting direction. I'm also really excited about text-based video games. So maybe you've heard of the NetHack learning environment, and I think this is a great direction for trying to do work in this space, kind of where you can keep on sampling out different interactions and experiences, and you have actions you can take within a reasonably closed space world. There's also a push towards training and evaluating multimodal agents. I think that, you know, this is one about trying to find the weather in Chicago on a particular day. I guess if you live in Portugal, you don't really need to know what the weather is because it's always going to be sunny. But if you live in Copenhagen, you need to know every hour of the day whether it's going to rain, and try to trust things along that direction. I also think that there should be a lot more work on multilingual learning and processing in that direction. And also thinking about multimodality for social good, because we know that these vision and language models are being deployed more widely throughout the world, and people are using them more and more in their daily life. And I think that we are starting to come into a lot of disinformation. I think that it will be interesting for us to study and understand what types of harms these models might be causing on society. And I'm just going to wrap up here by talking about a project we just finished on understanding sexism in a multimodal setting. So this is a project which is a collaboration between computer scientists and linguists and gender specialists. And this part of the talk contains sexist material, and I'm sorry about that. It will be marked in orange, so if you don't want to look at it, you don't need to. The motivation, so this is a Spanish language data set because that was the language skills of the people working in the project, but I'm confident that the findings we have here will apply to other languages as well. Online content is quite well known to radicalize people by presenting them with alternative and narrowly scoped worldviews. You can find reports on this by the European Union and many other organizations. And social media platforms like Facebook and Twitter have been taking steps to remove content moderation teams in favor of community notes. But the effectiveness of community notes is debatable. I think what we want to be able to have is to develop effective tools to detect and moderate the proliferation of harmful content. Not only does this support the work of human moderators, it also supports the work of human annotators who need to watch this type of harmful content and the effects it has on them. And so in this project, we focused on 4 different types of sexism. One was about stereotyping that you would find in TikTok videos on social media. The other was on sexism that denies the inequality of different genders. The other was on discrimination, where people were actively discriminating against people in videos. And the fourth was on the objectification of people, in this case, mostly women and LGBTQ identifying people. In addition to these 4 different types of sexism that we worked with, we also worked with non-sexist content because we want to know, does the model that we're trying to evaluate understand the difference between somebody reporting on sexism or maybe somebody talking about it with an ironic shift? And so this is also an example of the types of data we need our models to understand, because we shouldn't be flagging data in which people are talking about their experiences. And most prior work in this area has focused on misogyny and sexism in memes, where they have static single images. And there's been no work towards non-cisgender identities. And so that's also something we have in our data set, where we have a more broad spectrum of gender identities represented in our inputs. And some of the main challenges we have here is that sexism in social media is really complicated, because you see lots of use of indirect language like irony and sarcasm. And you also have this thing where many social media videos are actually commentary on clipped content that's sliced in. And so if you only have the context window to process half of the video, you might end up only processing the part in which somebody is reporting on sexism and not the person afterwards that's being really mean and disgusting about it. And you also end up with contradictions between verbal and nonverbal content, where if you watch the video, you get a very different impression from just reading the transcript. And so this is a data set of 400 videos straight from TikTok and BitChute. If you don't know what BitChute is, never visit it. Is the end of the internet. Our data is almost 50-50 sexist, non-sexist material. And it was scraped using a specific set of hashtags that were iterated on by the linguists and gender specialists within the project, where we were trying to, these are translated, so I don't have the original Spanish hashtags. And then we retrieved the videos using Apify in the BitChute download manager. And then we transcribed the speech using Whisper variant. We extracted the audio using FFmpeg, because sometimes you just have to go old school and use the terminal. And we used EasyOCR to extract the OCR out of the video data, because we kind of have this interesting multimodal problem. Most of the videos are around about 100 seconds or less, but some of them go up much longer. I don't know how anyone would have the patience to watch an 8-minute video on TikTok. So maybe that one's actually from BitChute. I'm not entirely sure there. And the annotation was done in a multi-stage process where we had 2 annotation teams of 3 people, where we had an expert annotator in each team, and each team annotated half of the data set. And then there were overlapping examples to measure inter-annotator agreement, which was about 78% Fleiss Kappa. And then in the actual annotation process later, we had a 3-step process to understand the relative importance of only being able to read the transcript, or also being able to listen to the audio and see the video. So we have a monomodal annotation and a multimodal annotation. And we did this for a binary classification task, so sexist, not sexist, or a fine-grained annotation, so going into those 4 different categories of sexism, and also for a segment marking, when they could look at the videos, Everything's cool. To mark where in the video the sexist language was occurring and exactly what type of sexism we saw there. In terms of the evaluation, we did zero-shot recognition of sexism using two different types of prompts. We had a simple prompt, and I'm keeping the Spanish original here. This was for the multimodal systems trying to detect sexism in the input. And we also had a much more detailed prompt where we tried to define exactly the different meanings we wanted to apply to stereotyping or denial of equality and all of the different discrimination types. And so when we look at the performance of, we have many models in the study, but here I'm just showing the strongest performing models. So the, this should say text. So the blue bar here on the left is text-only inputs. And you can see here reasonably comparable performance for Llama 3, Gemini 2 Flash, GPT-4o, and Claude 3.7. And when the dark blue bar is when you add in the richer definition of the different types of sexism. And the performance improves for almost every model except GPT-4o. And then when we work with the multimodal data, so we couldn't get Llama 3 vision model to work for this at all. I don't know if it's because it had a safety filter on it that wouldn't process the data. It's a bit unclear to me. But one interesting thing we see here, for example, with Gemini 2 Flash is when you give the multimodal inputs, the model performance starts dropping. So it's not doing a good job of processing the video and the audio data. But when you give it the richer definition of different types of sexism, it can recover some performance, whereas models like GPT-4o and Claude 3.7 can make much better use of the multimodal data and the richer definitions of what the different categories of sexism are that we would like it to understand and to be able to predict within the input. And I think this is an important area for people to work in. Ultimately, I'd like to see this type of project expand into some kind of system that will continuously learn by finding new examples on TikTok to train its classifiers better so that the 400 examples that we had to annotate in this don't need to be seen by anyone again for data collection and annotation purposes. So on that note, I'm going to finish. Today, we have covered 5 different aspects of multimodal learning, be it from data sets and tasks to representations, modeling strategies, types of understanding of how these models work, and new directions and frontiers in vision and language. Some people ask me this at the end of this type of lecture, so I'm just going to say it here. There are opportunities for people to move to Copenhagen if they want to. The weather is terrible, but the vibes are immaculate, I'm told. So there are 2 great places to go. The Danish Data Science Academy has application deadlines in June for PhD fellowships and postdoc fellowships. And the Danish Advanced Research Academy has application in August for PhD fellowships. Both of these types of scholarships are fully covered. It will cover your cost of living, your tuition, your accommodation, everything. You don't need to bring anything except for a great application. And you don't even need to apply to work with me. If there's somebody you want to work with in Denmark, you can use these types of application mechanisms to reach your goals. If you want to ask questions about this, come and talk to me. I'll be available during lunch. We all know the queue is going to be 35 to 100 minutes. So there's loads of time. And I also want to finish by thanking all of the people who did almost all of the research that I spoke about. I'm not the person that's responsible for this. I'm just helping to guide along the way, and these people are just as important. So I'll finish by thanking them and thanking you.
I don't. Is there somebody else? Just me. Okay, sorry. The example you gave about the interactions in the real world with the triangle and the 2 balls. Okay, can you hear me now? Okay, so the example you were talking about the interactions in the real world with the 2 balls and the triangle, is that assuming that you're actually using data-driven predictions, or is it
Yeah, can you please wait just a couple of minutes in order to finalize our Q&A, and then we can all go to have lunch and stay in the queue for forever. Thanks a lot.
So to pick up what I was saying, is that assuming more of a data-driven prediction, or are you also talking about actually incorporating a physics-informed machine learning?
It would be great to be able to incorporate a physics-informed machine learning model into this. I once spoke to some researchers from DeepMind about how you might do that, and they said, oh yeah, that's really hard because once you start building a really good physics simulator, then you've already done a lot of the work you'd want to do anyway. So I think at the time they were trying to do some work with Unity on trying to build these types of physical simulation environments. And I never saw anything come out of this direction, at least that was public facing. So, and actually what we've seen more recently from DeepMind in its London office is like trying to learn about physics of the world from video data directly. So I think that kind of gives intuition about where they think this is going.
Okay, because that's actually my area of work, where
Cool.
I actually use physics-informed models for like biomechanics and everything else, and then wrapping a machine learning and language models for actually creating a better interaction with the physics of simulations. So
That's super cool. I don't know if you have been working with data sets like this. Maybe you're doing much more complicated things.
I started from the physics side of things, so now I'm actually trying to bring in the
Yeah.
machine learning. So
Okay,
yeah.
super cool.
Hi, I'm here. Yes. Thank you for the talk. It's very insightful. I have a small question related to fusing text and images. So up until now, I think the approach is captioning, basically describe what's an image. But most of the time I see is all those data set, you have image that can be described in a very short text, right? Because in some of my domain, we work with very complicated images. Imagine a graph, and to understand a graph, you need 3 years of bachelor degree in economics or whatever. So when we read financial report, right, we have table and images that are very hard to describe. And the only way to deal with that right now is to use a dual model. One is a text parser model to read the table in Markdown, for example, and then use on top of that a VLM model to read the image again, just to have some idea about the layout. Do you think that is there any way in the near future to train or to deal with that problem in a more unified approach like you showed? Thank you.
I think so, yes. So most of the work I've seen, well, it's hard to know exactly what's happening behind it, but if you take a model like Qwen3 VL and you give it a piece of input, which is like a page from a book, it seems quite clear to me that it's doing OCR as a step along the way. I wonder if you've tried any of those types of models.
Yes, we try Quen 2.5 VLM and also small docklink, a lot of them, but they fail miserably when you fit them a table with nested columns.
Is there any way that you could create a reasonably large data set and just instruction tune it further on that one task to suit your need? I think that's basically the recipe to success that we're seeing. So people download a model from Hugging Face and think, oh, wow, this model can do OCR. Well, yeah, it was instruction tuned to do it. So
Maybe yes and no, but we hit a wall, so
I'm sorry to hear that. I think if you had some data that you could use for an instruction tuning, you could just break through that wall.
yeah. So maybe you're right. It's all about data set.
Yeah.
Yeah.
So I have two questions. One is about the content moderation. I'm really familiar with the problem because I've seen the commentaries like saying like these people that have to moderate content, they watch really harmful content. I'm talking about like animal abuse, like violence, like all the types of awful videos. And are you currently like working on like actually detecting violence from videos? I mean, this is a very touchy subject. but it would really help these people if this work was done like automatically by a machine and not by a human being. So not only like sexism, but also like the video part.
Currently, I'm not working on that. I do agree it's an important area for us to work on. And I do believe that companies are doing quite a lot of work that we don't see on trying to moderate some of this type of data. For example, after my brief visit to BitChute, I am more convinced than ever that if you think the YouTube filterer is bad, you have no idea about just how bad it could be. But I don't know how I could start working in the direction of detecting violent material. I actually can't imagine getting my university ethics board to it's really hard to work on sexism and to say we're going to watch hundreds, in this case, it was 11 hours of videos about sexism. That's difficult to convince people about the importance of this. Sorry,
Yes,
not the
yeah,
importance of it,
yes,
the
it's true. Like
viability.
it's really hard to like convince people to do this kind of research because it's like you have to have data sets of like violent videos, and that's not very like a nice thing to propose to someone. So maybe we will leave like this work for the corporations to maybe like do that internally, and they don't share the data with the world. So, um, but I had another question. So I think the detection of sexism can also have like some bad results, like for example, detecting like educational content on sexism, and that content may also be flagged and be eliminated by companies. So I was wondering, what is the precision of your methods, and yeah, basically if this educational content also gets targeted.
So I completely agree with you, and that's why we, in our annotation process, we have a way to mark the content as being non-sexist, and that this is non-sexist content that's about discrimination or it's about domestic violence, because people should be allowed to share that type of information online and not be flagged by an algorithm. And I think this is something we've actually seen in other parts of social media where people don't use particular words. So what is this one? I'm sorry, I'm not very social media savvy, but is it unalive? Do I have to say that word for this video to go on YouTube later? Because people have to change their language over time. And I guess that once people start changing their language, there's a never-ending kind of cycle here. But that's why we included these non-sexist annotations. It's not that the video has nothing to do with sexism. The video is about sexism, but it's not harmful. We haven't tried to annotate conspiracy theories in our data, but I guess so. I mean, I just haven't done it. It's going to be a neural network. The answer must be yes somewhere.
Do we have time for maybe one question?
We have -2 minutes.
So one last question, if you feel like you have a good question.
I'm sorry, but I have a question maybe. In real-time scenario that we have, for example, like a robot, that it should process everything in a moment. So even for very good models like ChatGPT or something like this, we have some latency problem. In this scenario, I think we couldn't use something like these models, even we have a good one. Sorry. So is there any technique for capturing important frames from the video to just process them?
Yeah, thanks for the question. So there are. You can do it just based on more simple statistics like the entropy of the different frames you see. Actually, video encoding strategies already include a lot of this information. So something like MPEG encoding is based on encoding an input frame and then an offset. And this is valid before you re-encode the next MPEG frame. So when you're encoding just the offsets, you're encoding deltas. So that could also be a way of trying to figure out what to encode. At the level of an actual individual image, I saw a lot of papers at CVPR this year on trying to shrink the number of patches you would need to give as inputs to a VLM based on the similarity of the embeddings of the patches and then fusing them together. So you could go from like maybe 1,000 patch inputs down to just 120 and get 98% of the performance of using the full input space. And with those types of strategies, you could definitely get closer to doing some kind of on-device learning, but not if you're working in some kind of area like medical learning where you're trying to remove tumors from people's skin or like, no. Go for the full old-fashioned human approach.